Hi, my name is Anna Meyer, and I'm presenting our paper, The Dataset Multiplicity Problem, How Unreliable Data Impacts Predictions. A standard machine learning pipeline starts with the training dataset and uses it to construct a machine learning model. Let's suppose we're going to build a model to predict employee salaries. This is just a toy example, but it is inspired by a real-world dataset, the American Community Survey. A common benchmark task in fair machine learning is to use data derived from the American Community Survey, including employment status, educational attainment, and demographic information, to predict whether an individual earns above or below $50,000. We'll consider the regression, not classification task for now. And let's suppose that this model predicts a salary of $60,000 for Bob. But what if I told you I have a different data set for the same prediction task, and that this data set is equally legitimate as the original data set? I'm purposely being a little vague on what legitimate means at the moment, but let's assume that domain experts and statisticians would not be able to definitively say which data set is more faithful to the world or more suited to the prediction task. This data set is going to produce a different model, and maybe this model says that Bob's salary is $70,000. Clearly, Bob would prefer this model if it's assigning his salary. But what if the company creating this model decides to go with the original data set? If you're Bob, you are going to be frustrated and disappointed and not know what to do. But we can ask, is this realistic? That is there commonly going to be a data set too that seems equally legitimate to the original data set? We argue yes, and that there's commonly a second or third or fourth or nth data set that's equally legitimate to the original one. We draw on prior work that discusses how data is not objective or unbiased, that it commonly contains errors, and that societal biases are reflected in the data. Let's walk through a few examples of how these data inaccuracies might occur. Suppose that this is our data set projected into 2 dimensions. What if someone, say Joe, was originally supposed to be in the dataset but did not answer his phone, and then some other person, say John, was included in his place? The original dataset, containing John, the blue point, is likely just as valid as the counterfactual dataset where Joe, the red point, was included instead. Or maybe the worker transcribing the survey respondents' results makes a mistake and writes down the wrong information. So in this case, the actual data set is the one with the red point, and the other equally valid data set is the one with the blue square. Those are just a couple examples of what could go wrong, but there are several other options for how data sets could be inaccurate or not fully representative of the world. As I said, problems with data sets have been documented in previous work. Our contribution is to frame this problem using the idea of multiplicity, that is, that there can be multiple equally legitimate data sets. The problem we propose is, given a large number of data sets that are equally good, and the set of models obtained by training with any of these data sets, what is the range of predictions for a given test sample? We can compute individual predictions for each of these models, and then find the range of predictions, which in this case spans from $58,000 to $70,000, giving us a range of $12,000. What we really care about is how large this range is. That is the prediction robust to dataset multiplicity? Let's suppose that we're okay with salary predictions differing by up to $5,000 across all of the models. In that case, the prediction for Bob is not robust to dataset multiplicity for these datasets and models. In the paper, we provide suggestions for what to do in situations like this where predictions are not robust to dataset multiplicity. The course of action will be context dependent, but options include finding a better original dataset to reduce the uncertainty and therefore reduce the number of other datasets we have to consider, or by choosing an alternate decision-making process, such as by having the model abstain on non-robust predictions. On the other hand, let's suppose that some of the model predictions were different, as indicated by the bold green predictions. Then, the range of predictions for Bob would be only $4,000. If we're still comfortable with a prediction range of $5,000, then Bob's prediction would be dataset multiplicity robust on this collection of datasets and models. That is, we would be confident that Bob's salary prediction was not significantly affected by errors in the training dataset. I've told you what our proposal for the dataset multiplicity problem looks like, but there are a few challenges to making dataset multiplicity robustness a useful metric. First, we have to know how to define two datasets as equally good. This problem is not one that we're able to solve directly because it will be very context-dependent and likely subjective. We hope our framing of the dataset multiplicity problem prompts discussions among stakeholders of what counterfactual datasets would be realistic in their domains. Second, we want to be able to efficiently compute the range of predictions for a test sample. It generally will not be feasible to enumerate all alternative datasets and train a model for each, because the number of datasets may be combinatorially large or even infinite. In our paper, we take a first step towards efficiently computing robustness to dataset multiplicity. Specifically, we look at linear models where there's label, noise, or uncertainty. Suppose, for example, that this is our dataset and the orange line is the best fit linear model. Our goal is to find the gray region. That is, all linear classifiers that could have been found instead had a small fixed proportion of the training labels changed. Our technique relies on the observation that the majority of the linear regression parameter theta can be pre-computed if all of the uncertainty is in the label vector. Our paper contains more details of how we can certify or disprove dataset multiplicity robustness. Next, we'll provide a teaser of our results, which is meant to provide intuition for how we imagine dataset multiplicity robustness could be used in a machine learning pipeline. We have two individuals here, real test points from the test dataset, and they agree on all features except for gender and occupation. For this example, we're going to consider classification with a $50,000 threshold rather than a regression task. To change the prediction for the first test point, we need to change over 2% of the labels. As long as the overall label confidence is high, say 99%, we will be comfortable with this robustness level. However, for the second test point, we find that we need to change only a few labels, about 0.1% of the training data, to get the opposite prediction. So this decision, under almost any reasonable belief in the label's trustworthiness, is not robust. In the paper, we provide more detailed experimental results across several datasets. We also explore how changing the definition of what datasets are equally similar affects dataset multiplicity robustness. For example, we might limit label inaccuracies to be in a subset of the data that we have reason to believe is less accurate. For instance, instead of considering the set of datasets where one salary has been changed, we might consider the set of datasets where one salary corresponding to a woman was changed. In the paper, we also discuss the importance of choosing these definitions in a way that makes sense for the particular domain. Thank you.